Hello, and welcome to this presentation about temporal tables, or system versioned tables, as the technical term is. We will talk today about temporal tables. What are they? We will look at how we can create a new temporal table or system versioned table. We will look at how we can take an existing table and make it system versioned. We will look at how we can migrate from some other temporal pattern for our data tier and how we can migrate that to use the built-in functionality for system versioning in SQL Server. And we will look at some performance considerations for system version tables, including both indexing and table designs. So what are temporal tables? Well, temporal tables are just tables to begin with. But what makes a table a temporal table in SQL Server is that you have enabled system versioning on the table. That means SQL Server is going to create another table which looks just the same as your main table, and this will be the history table. And you, or SQL Server, will also add a couple of rows to the table, a start date and an end date to the row in the table. Now for the current rows, they will be in your main table. They don't actually have an end date, but since null is a kind of special case in a database with a three-part logic to them, Microsoft decided that the end date for a current row is going to be the year 9999, 31st of December. And then in the history table, you will have a start date and an end date of a row. So that means when you do an update or you delete a row in the main table, you will get the previous version of the row stored in the history table, along with the start date, which is picked up from the main table, but also an end date. So, and this is done automatically for us under the hood. And this is useful for not all use cases, but for some. One is when we want to handle slowly changing dimensions in a data warehouse. It's very good if the source system has system versioning on the tables that we're going to use to load our dimensions, because then we can very easily know what's been changed since the last time we loaded a dimension, what's been added, and using that information, we can do reporting in our data warehouse, and we will know that if a customer, for example, has moved from one city to another, when we make a report from a specific point in time, we will know where that customer lived, which is of course useful in a reporting scenario. Other use cases could be, for example, a price list, which is what I will use in my demos for this presentation, to store price changes for products. So for example, using a system version table, we can use T-SQL and the special editions that came with system versioning for SQL Server. We can ask, what was the price of a pack of chewing gums 1.5 years ago? Which is very nice to have, because we don't need to create our own logic for it. SQL Server takes care of that for us. Before we jump over to the demos, a few words about me. My name is Magnus Ahlkvist. I live in Sweden. I have worked with SQL Server 20 plus years. I think 1999 was my first job when I used SQL Server. Back then I was a web developer, but I liked working in the back end, and I really liked working with databases. And I guess it's how the brain works. I like set-based logic. I always liked the mathematical logics and algebra in university. So it kind of comes natural for me to think the way databases think. I'm a senior consultant now with Transmocopter SQL AB, a SQL Server specialized consultancy firm. I am the organizer of an event called SQL Friday. It's a weekly event running on Fridays at noon Central European Time. It's running online, so just join the Teams call and listen to some really world-class top speakers presenting about SQL Server for us. I also do record the sessions and present them on YouTube a little later on. I am a data platform MVP. It says a little bit about my interest for SQL Server, but it says a lot about my interest for the community, which is partly why I really love working with SQL Server so much, because it's such a fantastic user community for the whole Microsoft data platform, but my end of it is working with SQL Server. So that's, I think, is all about slides that I have. And from now on, this presentation will be just demos. So we will jump over to Management Studio, my favorite tool, and we will look at how we can create new system version tables, how we can take existing tables from our databases and make them system versioned, how we can migrate if you have an existing temporal pattern implemented in your applications. How can we get rid of some of the code that we wrote ourselves to handle the versioning of tables and start using the automatic system versioning from SQL Server. And we will also look at some performance considerations. And it will be some views into execution plans, some views into indexing, but I will also show you a little bit how we can or maybe how we should remodel our database if we do system versioning. So from now on, as I said, we jump over to Management Studio and the rest will be demos. All right, we are in Management Studio and we will start the first section of the demos with creating a new system versioned table. A price list is a table that stores prices for products. And so I have a price list table here. It's not very well modeled, I must say, but this is what we have. We have a product ID, which is the primary key. We have a price. We have a product short name, like screwdriver or red bike, stuff like that, and a product description. Probably the product ID and the product short name and maybe even the product description will not change so much over time, but the price most probably will change. So if we want to keep track of the historical prices, which we do want to keep track of if we create a system that stores prices, we can make this table temporal or system versioned. To do that, we need to add some more information to this table when we create it. So we will create the table with 2 extra columns. these two extra columns will be the start time and the end time of a row in the table. So we can say valid start. This has to be of the data type date time 2. Any resolution goes, but it has to be a date time 2. Date time 2, and I'm going to choose the highest possible resolution, which goes down to 100 nanoseconds resolution. This cannot be null, and we can decorate it with generated always as row start. So this tells SQL Server that this column is not for a user to update. It's for you, SQL Server, to update for us. I always get this wrong about where to put the not null. It should come after generated always as row start, not before. So valid start, we also need a valid end. Same data type as valid start. So date time 2 with the resolution 7, which is the highest possible. It's generated always as row end, and it should not be null. We also need to define in the table what is our period for system time. And to me, it's a bit double information, because we already defined valid start and valid end as generated always as row start and row end. But we need to define the period for system time to be valid start and valid end. So almost done. There's one thing more we need to do when we create the table. We need the with clause. With system versioning equals on. And I could leave it at that. And if I now create the table, I will get a history table which SQL Server names for me. But I'm not going to be very fond of that name. So I will tell SQL Server what the history table should be named. DBO dot price list history. Now this will create a history table for me, which I can control the name of. If I don't name it, SQL Server will name it, and I think the name will be something like price list. Maybe it will contain the word history, but it will also be a hexadecimal representation of the object ID of the main table, which is not anything I would like. So let's create this table. It's done. We can look in Object Explorer now. In Data Platform Summit 2022 database, in the tables, we will see that we have the main table here. Object Explorer tells us that it is system versioned. And if we open it up, we will see the history table underneath. It doesn't mean that the history table is any other type of table. It's just a table. But in Object Explorer, SQL Server knows that price list history is the history table of the price list table. So it will show us this under the price list table. So it's kind of convenient. Maybe you also noticed the little clock symbol next to the name. This is also decoration by Object Explorer or Management Studio. So we know that this is a system versioned table. So I think we are ready now to add some data to the table. So let's do an insert. Insert into dbo.pricelist. What do we want to insert? We want to insert a product ID. We want to insert a price. We want to insert a product short name and a product description. We do not want to insert the valid start and the valid end because that is created automatically by SQL Server. And that's what this means. Generated always as row start. SQL Server won't even allow us to enter our own information in there. We need some values, of course. So values, we can use product ID 1, the price 10, product short name, pack of gums, and the product description. Since I make it an nvarchar, I should indicate that also on the string. Chewing gums, minty, delicious flavor. Okay, we have one row. I'm good with that. Let's look in the table. Select star from dbo.pricelist. We have a row with a price, with the product short name, with the product description, no surprise, and we have the valid start and also the valid end. So valid start is going to be exactly when the row hit the database, hit the table. And valid end is going to be 99, 99, 1231, kind of the max value for a date time 2 with this resolution. That's good. What next? Let's make an update to this product. Update dbo.pricelist set price equals 11, where product ID equals 1. And now we can look in the table. We will see that the table now reflects the new price, 11. We will see when we got that price. It was at 16:36, so 4:36 p.m. It's interesting. Oh, it's okay. It's 2016, so it's 8:16 p.m. When I look at the clock here, it's not actually 8:16 p.m. It's 2 hours later, but this is going to be UTC time. So remember that, UTC time on the valid start and valid end. Okay. What next? Let's look in the history table, because I told you that SQL Server is automatically going to keep track of the previous prices. So select start from dbo.pricelist history. And yes, there we have the old price. We have the old price of 10. And we also have the valid start and a valid end. Remember, it was 99, 99, 12, 31 on the current rows. So having a valid end, which is not year 99, 99, means this is not anymore a current row. So this price was set at 2015-24, and this price ended at 2016-36. And this is nice because we now can tell, let's say at 2016 exactly, what was the price at that time. Well, there are some addition to the T-SQL language that we can use to find out. So select star from dbo.priceList, and I would really like my IntelliSense to work. For system time as of, and here I will enter a specific time. So let's say 2022 08 29 2016. Let's leave it at that and see what was the price at this time. And we can see from the result the price was 10 at that time, which makes sense because 10 was a valid price between 2015-24 and 2016-36, and this time falls between those. So if we now look before the start time of the first historic row, we don't get a result because this product did not have a price at that time. If we now look at, let's look a bit into the future, 45 or 56. So as far as SQL Server knows, the price in 35 minutes is going to be 11 because that is the current price. And until we change it, SQL Server is going to think this will be the price for, well, until the end of time. Now let's have some fun. Let's delete the price. Delete from dbo.priceList where product ID equals 1. And now if we look in the price list table, it's going to be empty. If we look in the history table, we will now get 2 rows. So we know that for a little less than a minute, the price was 10. And then for 5 minutes or so, this period, the price was 11. After that, we don't have a price for product ID 1. But what if we made a mistake? We were not supposed to delete the price, or it wasn't a mistake. We took that product out of our assortment and now we want to put it back again because marketing decided that we should always sell chewing gums with minty delicious flavor. And they should also be on discount, so 9 will be the new price. So we will now insert a row again into the price list table. And now we still have the history and we have the new price. What's interesting here is that we will have a gap in history because the valid start is going to be this time 2022, and the valid end of the oldest historic price is 2021. So let's query now for what was the time at 2021-10. At that specific point in time, this product doesn't exist in the price list table. Not in the main table, and in the history table, there is no time span where this time falls between the start and the end. But let's look at 1 minute later. Well, then, okay, 2023. Then it's back again with the price of 9. So super useful to be able to query history for tables. for information that is in our tables. So price list is a good example. Other good examples could be measuring data from, let's say you get data from a weather station every minute. Just update, you have the weather station ID and just update the weather data, and the history table will keep track of all the data points and the history for them. So that is the first part of the demo. And in the second part of the demo, we will, instead of creating a new table which is already system versioned, we will look at a table which already contains data, and we will make it system versioned. And so what I want to do then is to start all over. I want to drop the price list table. I want to start over again. So let's try that. Drop table dbo.pricelist. But that will give us an error message saying drop table operation failed on this table because it's not a supported operation on a system versioned temporal table. So what we need to do is to break system versioning. Then we can drop the main table and the history table. And by the way, if I would try the same with the price list history to drop that one, I would get the same error message. So I need to alter table dbo.pricelist set system versioning equals off. Now I can drop the main table and I can drop the history table. Good. So now we can start over, and I'm going to take this DDL statement for the table. I'm just going to skip the valid start and so on and create a new table. It's going to be empty, so I'm going to add some information to it, and then we're going to make it system versioned when it already exists and has data in it. So let's insert some information. Insert into dbo.pricelist. I want to insert a product ID, a price, a product short name, and a product description. And the values should be 1, price 10. We still have pack of gums. And the description is going to be the same as before. So let's do copy paste, chewing gums, minty delicious flavors. All right. And then I'm going to add another row as well. Product ID 2, it has the price 100. It's a bike, red. Description is super fast racing bike. You could of course argue that if a pack of chewing gums costs 10, it's strange that a bike costs 100. But this is my world and my prices, so that's how it is. Let's do the insert. And now I want to make this a system version table. Because I designed the system, I realized that, hey, prices change, and I want to know what they were before. So what we then need to do is to alter the table, add the 2 columns for valid start and valid end. We need to define it, define the period for system time, and we need to alter the table and make it system versioned. So let's alter the table dbo.pricelist, add. What do we want to add? We want to add valid start as date time 2, generated always as row start, not null. Valid end date time 2 generated always as row end and not null. And we can add the period for system time as valid start and valid end. Very much like when we did it on creation time. So let's try to run this and see what happens. Well, alter table only allows columns to be added that can contain nulls, and we decided to not allow null because we cannot allow null if it's going to be generated always as row start. So then we need to do this. We need to define a default definition. Or the column being added as an identity or a timestamp column, and that's not what we do. If the table would have been completely empty, it would have been okay to do this, but it's not empty, it contains data. So we need to do a few things. We could define it as nullable, but then we cannot define the period for system time, etc. So we really stuck. What we need to do is to create default constraints. So let's do column constraints. Constraint df price list row valid start default, and the default value for the valid start, it's going to be a philosophical question. Is it now when I start system versioning, or is it when I started my company? I don't have the history for each product, so I need to set the same value for every row. Let's choose something. I'm going to choose the default date, which is 1900-01-01, I think. Yeah, that's the default date. So now we're done with the valid start. The row end, well, the valid end is easier. I'm going to prettify this code a little bit. Constraint df price list valid end default, and this has to be the max value for the data type that I chose, which is datetime 2 with resolution of 7. So 99, 99, 12, 31, 23, 59, 59, and then 7 nines. That's the default value. Now we can try to run it, and now it works. And now we need to enable system versioning. We defined the period for system time, we defined the valid start and valid end, and now we can alter table dbo.pricelist set system versioning equals on history table equals dbo.pricelist history. And now it's system versioned again. Now that we're done with this, we have the generated always as row start, we have the generated always as row end defined. So now we can drop the constraints. Alter table dbo.pricelist drop constraint df price list valid start, and we drop the valid end as well. Because it doesn't make sense to have a default constraint because it won't be used, and it will just be confusing to have a default constraint telling us that the start date should always be 1st of January 1900, but generated always as row start is going to make it now at the time when we insert or update the row. Therefore, it makes sense to drop the constraints, I think. So let's do a select from the table. And we have two rows. We have the start, 1st of January 1900. We have them valid because end date is 9999, 1231. And let's just make an update to see that the system versioning actually works. Update dvo.price list set price equals 9, where product ID equals 1. And we look into the history table, and we see that we have the historic row with the price 10 for the pack of gums. So this is how we take an existing table which is not system versioned and make it system versioned. Next step, we're going to level up a little bit, and we're going to look at a kind of normal pattern for system versioning where we have a start date, we have an end date in the table in itself. We don't have a history table, so rows and historic rows are stored in the same table, but you have the valid start and valid end in them. So we're gonna break that up, move the historic rows to a history table. We're gonna keep the current rows in the main table, and we're gonna enable system versioning on the table using the existing history table. So that's the next demo. So assuming we already have a table where we have implemented our own temporal pattern, it could look something like this. We have a product ID, the price, the product short name, and the product description as before. We have a valid start, and we're going to use the data type date time because I'm assuming we implemented this some years ago when date time was the go-to data type for dates. So we're going to use date time. It can't be nullable. It has a default value of current timestamp, which means now when the row is created. And the temporal pattern we have used, which there is some support for in some kind of usable components in .NET, we have the valid end set to null. So for a current row, the end date is null. And we store the history inside the main table. So current rows has valid end equals null, and all the other rows has valid end set to some date when the row was invalidated. And we insert some data to kind of mimic that we have a history. So I have just one product, and I set the price to 10, and then change it to 11 and 12 and 13, which will be the kind of current price. So let's create this table with some data in it, and let's have a look at it. So when we decide that we want to migrate from an old temporal pattern to use system versioning for temporal, we have this data in the table. And with system versioning as SQL Server, history has to be in a separate table. So that's the first thing we need to do. Move the historic rows to their own table. And I'm going to do it with a simple select into statement. Select into dbo.pricelist history from dbo.pricelist where valid end is not null. So that gives us 3 rows that goes into the history table, and then we delete those rows from the main table. So now we have split the data into main table having current rows, and history table has historic rows. That's step 1. Let's look at the data. We have 1 row in the main table, 3 rows in the history table, with a valid start and valid end. Now the table, since we cannot have product ID as the primary key in this old temporal pattern, and therefore I created the table with product ID and valid start being the primary key together. So we need to change this. Now that the main table will actually have product ID as the primary key, the natural key, we will drop the primary key and recreate it. We will also drop the default constraint that is used for valid start. So we drop the default constraint, we drop the primary key, we create a new primary key with only the product ID in it. And that's okay now because we moved all the historic rows to the history table. So now we've done that. We need to fix the data types because with system versioning, the data types for row start and row end has to be datetime 2. So we alter the table, update the rows, or update the columns to be datetime 2. This is a thing, we need to have the valid end as a nullable column because it does contain a null value for now. So the start can't be null because, well, we can keep it as not null because it has data in it. The end date does not have any data, it's null, and therefore we need to make it nullable initially. Then we will update the end to max the max value of the data type we chose for valid end, which is 99, 99, 12, 31. You know it, we've seen it. So let's update the existing rows. And now we need to alter the column again and make it not nullable. And why do I first change data types, then update the value, and then change it to not null again? Well, if I would do the update of it to set the value first, the resolution of date time is just 3 digits for milliseconds. And also date time, if I would try to set the value to 23, 59, 59, 999, it would fail because this would be rounded to the next second, and that would make an overflow of it because it would be the year 10,000, which is too big. So therefore, we have to first set the data type to datetime 2, then update the value, and then we set the column to be not nullable. So now that that's done, we add a period for system time, valid start and valid end. And you probably noticed we didn't do the generated always as yada yada. That comes with the territory when we add the period for system time. So now that we have added the period for system time, we are ready to enable system versioning. the main table is ready for it. The history table still has some updates to do. We need to alter the columns valid start and valid end and set the correct data type to them, datetime 2. So a few steps. If the table is very, very big, all these steps are going to take some time because you update the data, and not only metadata, you actually have to update the actual data, because I made the date columns bigger. Date time has a quite low resolution and doesn't use as many bytes as a datetime 2 with a resolution of 7. And therefore, all these alter table statements will actually do some page splits and move data around if the table is big. So this is an operation that is not done online. You have to stop incoming transactions to the tables, and then you can enable system versioning on an existing temporal pattern. Now we enable system versioning with the history table being the existing table with data in it. And now we can look at the tables, and let's just make an update to the price. Update price list, set price equals 14, where product ID equals 1. And have a look again and see that indeed the price 13, which was just recently the current price, is now in the history table with an end date of, well, just recently. So these are the steps you need to take to implement or migrate to system versioning in SQL Server if you already have a temporal pattern, but implemented with your own code, so to say. The last piece of the demo section is going to be about performance. And what we will look at is the indexes on your history table, and possible indexes you should add maybe to the main table, and also some advice about table design. I purposely made this table a kind of bad design, and I'll tell you why. So let's do the last demo before we wrap up. Let's start looking at indexes for the history table. In Object Explorer, we see the table, and I've expanded the indexes tab. And we see that we have an index called IX price list history, and it's a clustered index. So we're now on the history table. This is what SQL Server creates automatically for us when we let the system versioning create the history table for us. So it's a clustered index. It's going to contain the valid start and the valid end columns, and that's the indexes we get. And that might not really be enough. In our example, where we have just one product, it doesn't matter. We're going to do a clustered index scan every time anyway, more or less. So, but let's say you have 1 million products, each having history. When you query for one specific product and you enter a date span that you want to look in. So let's say you want to see price list changes that occurred between yesterday and today. This index is going to be very expensive to use because it's going to scan all the data between yesterday and today. And then it's going to apply the filter because you only search for one product. So it's going to look in history for all the price changes within a time span and then apply the filter for the product ID. But this is the indexing we get. Sometimes it's really good enough. Sometimes it's not. If you want to load a dimension and find out which changes occurred to this source table in a period of time, it's a very good index. But if you want to include the columns which is the primary key in the main table in your predicates when you search for a time series or a time span, then it's not going to be very useful. So depending on how you will use your table, how you will query your history for data, that's going to decide if you want to add more indexes or not to the history table and which they will be. So just bear in mind that what you get out of the box is a clustered index on valid start and valid end, a compound clustered index. This index, as you can see from querying sys.partitions, is going to have page compression enabled, which I like. Page compression, with very few exceptions, is always going to be beneficial. And the history table is going to store more data probably than the main table if it's a table that is updated often. So then page compression can save you some disk, and therefore if the data is stored on disk with compression, that means it's going to load into the buffer cache with compression as well, meaning you can fit more rows into the buffer cache. And the worst thing for a database is to have to do disk I/O. It's expensive. Even with fast disks, it's going to be an expensive operation. So if you can fit more pages into the buffer cache, it's going to mean less read I/O from disk. So therefore, page compression is a good idea. But you will probably want to add indexes to your history table if you're going to read it. So keep that in mind. The other performance consideration I want to point at is table design. In this case, we have a price list. I have only updated the price. And really, it's not really just price list information we have. We have the product short name and we have the product description included here. So it's really a product table with a list price for the products. When you make an update to just the price column, you're going to take a copy of the whole row and put it into the history table. But what if you never change the short name and the product description? Is it really a good idea to duplicate that information every time you want to update the price? I think not. And therefore, I would split this table to keep the static information about the product in one table, which is not system versioned, and the not static information about the product would go into this price list table, which would be system versioned. So keep the system versioned table as narrow as you can. to not waste disk, to not have to write more than necessary to disk. Because even if disk is super cheap, it's just unnecessary to duplicate the same information over and over. Also, if you do change the product short name and you do change the product description, it can still be a good idea to split this table into two. Because if you make a change to the price, but not change the product short name or the product description at the same time, it still means you duplicate the information that didn't change. And I would assume that the product short name and the product description, that's going to be changed by product managers in the marketing department, while the price is going to be changed by someone else. And the changes to price and the changes to the descriptions, they're going to be kept apart in reporting when you query your tables to see when did I change the description for this product and what was the previous value. That's going to be another reporting situation than what was the price history of this table. And therefore, I would argue that you should still split the table, even if all the columns are updatable or will be updated. Keep those changes separate into different history tables. And to do that, you need to split the main table as well. There are quite many applications where you store information in a row. It could be a very wide table with many columns, and you store it once and then you update the status flag. So let's say for a shipping system, you get a lot of information about an order or an order line. And then you have a status which indicates that it's received by the warehouse system. It's picked, it's packed, it's shipped, it's delivered, it's even invoiced. Information like that with one status column. So if you implement system versioning for such a table, you're going to waste a huge amount of space because you make a copy of all the columns in this wide table when the only thing that ever changed was the status flag. So if you're going to implement system versioning, consider which columns in the table will change and try to move them out to another table. It will mean a join if you need the whole information about a row or about an entity, but it may very well be worth it, because even if it's done automatically, all this versioning, it still means that SQL Server has to, when you update a row, SQL Server has to look at the row, take a copy of it, write it to the history table, but with another end date. So if it's a wide table, it's going to be a lot of information that is written to the history table, and then the actual update to the main table happens. Same thing if you do a delete. You have to move the information to another table, and that is a write operation. It does not come for free. And it's completely unnecessary to allocate lots of pages in the history table for information that never changed. So keep that in mind. Thank you for listening. And thank you so much, Data Platform Geeks and SQL Server Geeks, for organizing Data Platform Summit. It is, as usual, super good content and well organized. Thank you, Microsoft, for sponsoring the event. It's impossible to run an event of this size without having the backup of a sponsor. So thank you for that, Microsoft. And thank you again for attending. There are some prizes that you can win when attending this event. One is to post a selfie with the hashtag DPS 2022 to social media. I use Twitter. I don't know what you use. You can give session and conference feedback. Conference feedback is really good for the organizers so that they can continuously improve. And session feedback is very, very valuable for me as a speaker. What did I do well? What did I not do so well? What can I do to improve? Please use also the free text fields to tell me why. If you give me 5 stars, I'm going to be super happy. But if you give me 2 stars and you tell me what didn't meet your expectations, that's going to be more valuable to me than just the pat on the back saying you liked the session. And you can also visit the sponsors and exhibitors in the exhibition hall, virtual, but still. So go there, talk to the sponsors, and you'll get a chance to also there win some nice prizes. Thank you again for attending. I hope to see you again. I hope to see some of you in person. And I am pretty sure I will see some of you in virtual life again as well. So thank you for attending. See you next time.